Hello everyone, welcome to this video. In this video, we are going to see how to solve the third type of nonlinear PDE. So in type 3, actually there are three forms. The first form is f of z comma p comma q is equal to 0. That is, along with p and q, if we have z, how to find its solution. So here the solution is assumed as z is equal to f of x plus ay. So if we take this x plus ay as u, we have z as a function of u, which means z is a function of u, but u is a function of x and y. So for differentiating z with respect to x partially, dou z by dou x can be obtained as dz by du. First we differentiate z with respect to u and then that u with respect to x. So it is dou u by dou x. But here it is dou u by dou x is, since u is x plus ay, dou u by dou x is 1 and dou u by dou y is a. So here dou u by dou x is taken as 1. So dou z by dou x is nothing but equal to dz by du. Similarly, differentiation of z partially with respect to y means first we have to differentiate z with respect to u and then u with respect to y partially. So it is dz by du into dou u by dou y. But dou u by dou y is a. So replacing dou u by dou y here, we get dou z by dou y as a into dz by du. So here we substitute p as dz by du and q as a into dz by du in the given equation. So from this we get dz by du as function of z comma a. Now integrating this with respect to the variable on either side, we get this complete solution as f of z comma a is equal to u plus c, where finally this u can be replaced by x plus ay. So which is the form of complete solution, and the singular and general solutions are obtained as usual. So suppose if we have the second form of PDE, like function of x comma p comma q is equal to 0. So in the first form we had z. In place of z, if we have suppose x along with p and q, here we assume that q was a. Actually, since z is a function of x and y, from this we can write the total differential dz as dou z by dou x into dx plus dou z by dou y into dy, which means p dx plus q dy. So we have dz as p dx plus q dy. So if we have this form of PDE, here we take q as a. So if you take q as a here, this dz becomes in this form. Now integrating this, we get our complete solution as in this form. Z is equal to f of x comma a plus ay plus c, and singular and general solutions are obtained as usual. Suppose if we have the third form of PDE, like f of y comma p comma q is equal to 0. So in place of z, if we have suppose y along with p and q, since z is a function of x and y, dz is p dx plus q dy. So in this form, we assume that p is equal to a. So in the previous form, that is, if we have x along with p and q, we take q as a. Suppose if we have y along with p and q, you take p as a. So if you replace p as a, you get this as dz. Now integrating this, we get our complete solution in this form, and singular and general solutions are obtained as usual. So now we are going to see some examples for this third type of nonlinear PDE. So here this is what our first example. So here along with P and Q, I'm having Z. So clearly we can say that this is the type 3 form of PDE. In type 3, this is the first form, right? So this is type 3 form 1. So in this we assume that z is function of u, that is z is function of u, that is z is f of x plus ay. So because of this assumption we get p as dz by du and q as a into dz by du. So now substituting this in the given equation 1, we get z is equal to dz by du the whole squared plus a into dz by du the whole square. That is z is equal to dz by du the whole square into 1 plus a square. So from this we get z by 1 plus a square is equal to dz by du the whole square. Now taking square root on both sides we get root z by square root of 1 plus a square is equal to dz by du. So now separating the variables, that is u one side and z in the other side, we get root z, that is 1 by root z into dz is equal to du by square root of 1 plus a square. So now integrating this with respect to the variable, we get in the left hand side it is z power minus half, z power minus half into dz. So when you take this root z to the numerator, it comes as z power minus half. So now we are integrating this with respect to z, and in the right hand side it is a constant term, that is 1 by square root of 1 plus a square is the constant term, and here it is integration of du. So now integral of this is nothing but z power minus half plus 1 by minus half plus 1, that is z power half by half, which is nothing but 2 root z, and in the right hand side we have 1 by square root of 1 plus a square into u plus some constant c. So since it involves only two arbitrary constants, so which is what our complete solution. So this is what our complete solution. So in this we can replace u as x plus ay, x plus ay. So which is what our complete solution. And now differentiating this partially with respect to the arbitrary constants. First, suppose if we differentiate this with respect to c partially, with respect to c partially, we get 0 is equal to 1, which is absurd, which means this has no singular solution. So type 3 form has no singular solution, and the general solution is obtained as usual. So now we'll see the second problem. So here we have p is equal to 2qx. So along with p and q we have x. So this is type 3 second form, form 2. So here we consider dz as p dx plus q dy, as that is a function of x and y. So here we assume that q is equal to a. So if we take q is equal to a in the given equation and solving for p, we get, that is if we substitute q is equal to a in the given equation, we get p is equal to 2ax. From this, that is this is what our p. So now we can replace p and q in 2 in 2. So dz is obtained as 2ax dx plus a into dy. So now on integration we get the complete solution. So on integration, in the left hand side it is integral dz, and in the right hand side it is 2a into integral x into dx plus a into integral dy. So on integration we get, in the left hand side it is z, and in the right hand side it is 2a x square by 2. So 2 gets cancelled here, plus a into y plus some constant c. That is z is equal to a x square plus ay plus c. So this is what our complete solution, since it involves only two arbitrary constants a and c. And when you differentiate this partially with respect to the arbitrary constant, first with respect to c we get 0 is equal to 1, which is absurd, which means it has no singular solution. It has no singular solution. And the general solution is obtained by taking c as function of a. That is, if we take c as function of a here, we get z as ax square plus ay plus function of a. So now differentiating this partially with respect to a, we get 0 is equal to x square plus y plus f dash of a. So elimination of a from these two gives, so elimination of a from 3 and 4. From 3 and 4 we get our general solution. We get our general solution. So now we'll move on to the next problem. So this is what our third example. We have to solve PQ is equal to Y. So here along with P and Q we have Y. So this is third form of type 3 equation. So type 3 and form 3. So here also we consider dz as P dx plus Q dy, and here, if here in this equation we have Y, so here we assume that P as A. So take P as A here, take P as A and then solve for Q. So take P is equal to A in the given equation 1. Then we get AQ is equal to Y. So from this Q is equal to Y by A. So now substituting P and Q in 2, we get dz is equal to a dx plus y by a into dy. So now integrating this, we get, in the left hand side it is integral dz, and in the right hand side it is a into dx plus 1 by a into integral y dy. So on integration we get z is equal to a into x plus 1 by a into y square by 2 plus some constant c. So which is the complete solution of the given equation. And when you differentiate this partially with respect to c, we get 1 is equal to, sorry, 0 is equal to 1, which is absurd, which means it has no singular solution. And for the general solution we have to follow the same procedure, that is, we consider c as function of a in that complete solution. Taking c as function of a in the complete solution, we get z is equal to ax plus y square by 2a plus function of a. And now differentiating this partially with respect to a, and then elimination of a gives our general solution. So differentiating 4 partially with respect to a, with respect to A, and then elimination of A gives the general solution. I hope you understand how to solve third type of nonlinear PDE. So we'll meet in our next video. Thank you.